Welcome to our complete and free tutorial on regression analysis. It's been 3 years since our first full course on regression analysis, and after nearly 1 million views, we thought it was time for a fully revised and updated version for 2025. This tutorial combines 4 essential lessons into one comprehensive guide. First, we'll start with an overview of regression analysis, where we will break down the fundamentals and explore its real-world application. Next, we'll dive into simple linear regression, where you will learn how to model the relationship between two variables. Then we will move on to the multiple linear regression, where we extend the model to include multiple predictors, making our predictions more powerful. And finally, we'll cover logistic regression, which is essential when working with categorical variables, like predicting whether something will happen or not. By the end of this tutorial, you will have a solid understanding of regression analysis and how to apply it effectively. Let's get started. If you like, you can find the content of this video in our book, Statistics Made Easy. So let's get started with the first question. What is a regression analysis? A regression analysis is a method for modeling relationships between variables. It makes it possible to infer or predict a variable based on one or more other variables. Let's say you want to find out what influences a person's salary. For example, you could take the highest level of education, the weekly working hours, and the age of a person. You could now investigate whether these 3 variables have an influence on the salary of a person. If they do, you can predict a person's salary by taking the highest level of education, the weekly working hours, and a person's age. The variable we want to infer or predict is called the dependent variable. The variables used for prediction are called independent variables. Depending on your field, independent variables may also be called predictor variables or input variables, while the dependent variable might be referred to as the response, output, or target variable. Okay, but when do we use a regression analysis? Regression analysis can be used to achieve 2 goals. You can measure the influence of one variable or several variables on another variable, or you can predict a variable based on other variables. Let's go through some examples. Let's start by measuring the influence of one or more variables on another. In the context of your research, you may be interested in understanding the factors that influence children's ability to concentrate. Specifically, you aim to determine whether certain parameters have a positive or negative impact on their concentration. But in this case, you're not interested in predicting children's ability to concentrate. Or you could investigate whether the educational level of the parents and the place of residence have an influence on the future educational level of children. This area is therefore very research-based and has many applications in social and economic sciences. The second area, using regression for predictions, is more application-oriented. To get the most out of hospital occupancy, you might be interested in how long a patient will stay in the hospital. So based on the characteristics of the prospective patient, such as age, reason for stay, and pre-existing conditions, you want to know how long that person is likely to stay in the hospital. Based on this prediction, bed planning can then be optimized. Or as an operator of an online store, you are very interested in which product a person is most likely to buy. You want to suggest this product to the visitor in order to increase the sales of the online store. The second point is highly application-oriented, focusing on making predictions to enhance efficiency. Okay, great. Now there are different types of regression analysis. There is the simple linear, multiple linear, and logistic regression. In simple linear regression, we use just one independent variable to predict the dependent variable. For example, if we want to predict a person's salary, we use only one variable, either if a person has studied or not, the weekly working hours, or the age of a person. Multiple linear regression, on the other hand, uses several independent variables to predict or infer the dependent variable, i.e. the highest level of education, the number of hours worked per week, and the age of the person. Therefore, the difference between a simple and a multiple regression is that in one case only one independent variable is used and in the other case several. Both have in common that the dependent variable is metric. Metric variables are, for example, the salary of a person, the body size, or the electricity consumption. In contrast, logistic regression is used when you have a categorical dependent variable. Categorical variables are, for example, if a person is at risk of burnout or not, if a person is diseased or not, or type of animal. However, the most common form of logistic regression is the so-called binary logistic regression. In this case, the outcome variable is binary, meaning it has two possible values like yes or no, success or failure, or diseased and not diseased. Therefore, in linear regression, the dependent variable is a metric variable, while in logistic regression, it is a categorical variable, also known as nominal variable. But what about the independent variables? In all cases, the level of measurement of the independent variables can be nominal, ordinal, or metric. Okay, actually in regression you can only use categorical variables with two categories or levels, such as gender with male and female. In this case, we can code one category with 0 and the other with 1. However, if a variable has more than two categories, like vehicle type, there's an easy solution. We create dummy variables. Don't worry, we'll explain more about dummy variables later in this playlist. Okay, a quick recap. There is the simple linear regression. A question could be, does the weekly working time have an impact on the hourly wage of employees? Here we only have one independent variable. There is the multiple linear regression. Do the weekly working hours and the age of employees have an influence on the hourly wage? Here we have at least two independent variables, in this case weekly working hours and age. And the last case, logistic regression. Do the weekly working hours and the age of employees have an influence on the probability that they are at risk of burnout, where burnout at risk has the categories yes or no? Now that we've covered the basics of regression analysis and its applications, let's take a closer look at the simple linear regression. This technique helps us to understand the relationship between two variables, allowing us to predict one based on the other. In the next section, we'll break down how it works and go through a real example and show you how to interpret the results. Let's get started. What is a simple linear regression? Simple linear regression is a method to understand the relationship between two variables. You can infer or predict a variable based on another variable. For example, you can predict the annual salary of a person based on the years of work experience. So a simple linear regression can help us understand how salary changes with an increase in years of experience. The variable we want to infer or predict is called the dependent variable. The variable we use for prediction is called independent variable. Let's look at an example. Imagine we want to predict house prices. The dependent variable, the one we want to predict, is, of course, the price of the house. The independent variable, the one we use to make the prediction, could be the size of the house in square feet. Of course, you can also use more than one independent variable. For example, the construction year or features like whether the house has a swimming pool, the number of bathrooms, and the house size. But in this case, it would be a multiple linear regression because you have more than one independent variable. More on that in my video about multiple linear regression. Okay, but how do we calculate a simple linear regression? First of all, we need data. So we collect information from 10 houses, including their size in square feet and the price they were sold for. Now we can use this data to calculate our regression model. Here, y is the dependent variable house price and x is the independent variable house size. And we want to use our data to determine the coefficient b and a. But how do we do that? Let's visualize our data using a scatter plot. On the x-axis, we plot our independent variable, the house size, and on the y-axis, we plot the dependent variable, the house price. Each point is therefore one house with the respective house size and the house price. Okay, now we want to summarize all this data using a simple linear regression. To do this, we draw a straight line through the points on the scatter plot. But the line we draw isn't just any random line. It's the line that tries to minimize the error or the distance between the actual data points and the line itself. If we add up the length of all the red lines, we get the total error. Our goal is to find the regression line that minimizes this error. But how do we actually calculate this line? This is where the equation of the linear regression comes into play. In the equation, b is the slope of the line. The slope shows how much the house price changes if the house size increases by 1 square foot. A is the y-intercept, telling us where the line crosses the y-axis. So if we have a house with a size of 0, the model will predict a house price of A. Of course, predicting the price of a house with 0 size doesn't make sense. However, every model is a simplification of the real world, and in the case of simple linear regression, our model is defined by a regression line with a specific slope b and an intercept a. Let's look at this example. In that case, our intercept is 100, so we enter 100 for a. But how do we read the slope? For this, we take a 1-unit step in the independent variable. For example, if we move from 1 to 2, then we observe how much the dependent variable changes with this 1-unit increase. In this case, if the independent variable increases by 1 unit, the dependent variable increases by 50 units. So our b is 50. Okay, but how do we calculate b and a? There are 2 ways to do this. We can calculate them by hand or using statistical software like DataTab. Let's look at this example. How can we calculate b and a by hand? To calculate the slope b, we use this formula. R is the correlation coefficient between x and y, so in our case the correlation between house size and house price. We get a correlation coefficient of 0.92. As y is the standard deviation of the dependent variable house price, and as x is the standard deviation of the independent variable, so house size, so in this case our b is 108.35. Here's a quick side note for anyone who wants to follow along and recalculate the example. There are 2 slightly different formulas for standard deviation. One divides by n and the other by n-1. Without diving into the details now, almost all statistical software uses the formula with n-1 to calculate the standard deviation. However, for calculating the regression coefficient b, we use the formula that divides by n. If you like a more detailed explanation of the standard deviation, feel free to check out my video on that topic. Alright, once we've calculated b, we can find the intercept a using this formula. Here, y bar represents the mean of the house prices, b is the slope we just calculated, and x bar is the mean of the house sizes. Substituting these values, the intercept a comes out to be 60,919.44. So based on this data, we have now calculated the coefficient b and a. If we insert the numbers for b and a, we get this equation. If we enter 0 for x, the house size, we get 60,919.44, which is our intercept. If we increase the house size by 1 square foot each time, we get a house price that is $108.35 higher each time. Okay, before we start with the last important topic, the assumptions for a simple linear regression, let's check the results with DataTab. If you like, you can load this sample dataset. The link is in the video description. We want to calculate a regression, so we click on Regression. Here we can now select our dependent variable house price and the independent variable house size. Now let's look at the results. We will focus on this table, which shows the key information we need. If you're curious about the other tables, you can click on AI interpretation for the corresponding table or check out our video on multiple linear regression, where we explain these details in depth. Okay, in this table we can see the calculated regression coefficients for the constant. We called it intercept and house size. The values match exactly with the ones we calculated by hand, the intercept and the slope. In the results table for a linear regression, you'll also see the p-value. What does the p-value tell us? The p-value helps determine whether the relationship between the independent variable and the dependent variable is statistically significant. To test whether the relationship we observe is meaningful or just due to random chance, we start by stating the null hypothesis. There is no relationship between the independent variable and the dependent variable. If the p-value is small, typically smaller than 0.05, we reject the null hypothesis. This is suggesting a significant relationship between the variables. If the p-value is large, typically greater than 0.05, we fail to reject the null hypothesis, indicating the observed data may have occurred by chance with no strong evidence for a relationship. So in our case, the p-value is highly significant, indicating strong evidence of a relationship between house price and size. Alright, in this example it's pretty obvious. A bigger house size typically costs more. However, there are cases where the relationship isn't that clear. And what about the assumptions? Here are the key assumptions. Number 1, linear relationship. In linear regression, a straight line is drawn through the data. This straight line should represent all points as good as possible. If the relation is non-linear, the straight line cannot fulfill this requirement. Number 2, independence of errors. The errors, so the differences between actual and predicted values, should be independent of each other. This means that the error of one point doesn't affect another. Number 3, homoscedasticity or equivariance of errors. If we plot the errors on the y-axis and the dependent variable on the x-axis, their spread should be roughly the same across all values of x. In other words, the variance of the error should remain constant. In this case, the assumption is fulfilled. But what about that case? Here we observe unequal variance. At low values of x, the errors are small, while at high values, the variance of the errors becomes much larger. Number 4, normally distributed errors. The errors should be normally distributed. The normality of the error can be tested both analytically and graphically. However, be cautious with analytical tests. For small samples, they often indicate normality, and with large samples, they quickly become significant. Because of these limitations, graphical methods such as the QQ plot are more commonly used today. If you use DataTab, you just need to click here to check the assumptions. So let's just go through how the assumptions are checked in practice. To check for a linear relationship, you can use a scatter plot. Plot the independent variable against the dependent variable. If the points form a clear straight line pattern, a linear relationship exists. If not, the relationship is likely nonlinear. In our case, we observe a clear linear relationship. To test if the errors are normally distributed, you can use a QQ plot or one of the several analytical tests. With a QQ plot, the residuals should fall roughly along a straight line, indicating normality. If you use an analytical test, check whether the calculated p-value is greater than 0.05. If it is not, there is evidence that the data are not normally distributed. The choice of test often depends on your field of research. However, as mentioned, the QQ plot is increasingly preferred as a visual and intuitive way to assess normality. Independence of errors can be tested using the Durbin-Watson test, which checks for autocorrelation in the residuals. If the calculated p-value is greater than 0.05, it indicates that there is no significant autocorrelation in the residuals and the independence assumption is likely satisfied. Homoscedasticity can be checked using a residual plot, where the predicted values are plotted on the x-axis and the residuals or errors on the y-axis. The residuals should show a consistent spread across the plot. A funnel shape indicates heteroscedasticity, meaning the variance is not constant. In our case, the plot looks acceptable, though not perfect. If these assumptions are violated, the regression results might not be reliable or meaningful, and the predictions could be inaccurate. So always check these assumptions before drawing conclusions from a regression model. So far, we've seen how simple linear regression helps us model the relationship between two variables, one dependent and one independent. But what if we have more than one factor influencing our outcome? That's where multiple linear regression comes in. In the next section, we'll extend our regression model to including multiple predictors, making our predictions more accurate and realistic. Let's dive in. What is a multiple linear regression? A multiple linear regression is a method for modeling relationships between variables. It makes it possible to infer or predict a variable based on other variables. An example. Let's say you want to find out what influences a person's salary. You take the highest level of education, the weekly working hours, and the age of a person. You now investigate whether these three variables have an influence on the salary of a person. If they do, you can predict a person's salary by taking the highest educational level, the weekly working hours, and a person's age. The variables we use for prediction are called independent variables. The variable we want to infer or predict is called the dependent variable. But what is the difference between a simple linear and a multiple linear regression? As we know from the previous video, in simple linear regression, we use just one independent variable to predict the dependent variable. For example, if we want to predict a person's salary, we use either if a person has studied or not, the weekly working hours, or the age of a person. Multiple linear regression, on the other hand, uses several independent variables to predict or infer the dependent variable. Therefore, the difference between a simple and a multiple linear regression is that in one case only one independent variable is used, and in the other case several. Both have in common that the dependent variable is metric. Metric variables are, for example, the salary of a person, the body size, or the electricity consumption. So unlike simple linear regression, multiple linear regression can include two or more independent variables. But what impact does that have on the regression equation? In the case of linear regression, this was our equation. We had one dependent variable y and one independent variable x. Now in multiple linear regression, we have more than one independent variable. But don't worry, the coefficients b and a are interpreted similarly to those in a simple linear regression. If all independent variables are 0, the value a is obtained, so we get a value of a for the dependent variable y. Furthermore, if an independent variable increases by 1 unit, the associated coefficient b indicates the corresponding change in the dependent variable. Okay, let's make one small adjustment. Going forward, instead of y, we'll use y hat. But why? In the previous video, we learned that regression aims to model the dependent variable as accurately as possible. However, when working with real-world data, there's always some error. In other words, the true values often differ from the predictions. Now, y hat represents the predicted values from the regression model, while y denotes the observed actual values. Great, you're gradually becoming an expert. Now there are 4 topics to cover: the assumptions of regression, how to calculate a regression with data tab, how to interpret the results, and finally, how to handle categorical variables in regression by creating dummy variables. Let's start with the first topic. So, what are the assumptions? The first 4 assumptions of multiple linear regression are similar to those of simple linear regression, but there is an additional 5th assumption. Let's briefly recap the first 4 assumptions and then we'll go into more details on the 5th assumption. Let's start with the first one, linear relationship. In the case of the simple linear regression, we were able to test this assumption easily. A straight line is drawn through the data. This straight line should represent all points as good as possible. If the relationship is nonlinear, the straight line cannot fulfill this requirement. In simple linear regression, we have one independent variable and one dependent variable, making it straightforward to plot the data points and the regression line. In contrast, multiple linear regression involves multiple independent variables, which complicates the visualization. However, you can still plot each independent variable separately against the dependent variable to gain an initial sense of whether a linear relationship might exist. Number 2, independence of errors. The errors, so the differences between actual and predicted values, should be independent of each other. This means that the error of one point doesn't affect another one. We can test this with the Durbin-Watson test. Number 3, homoscedasticity or equal variance of errors. If we plot the errors on the y-axis and the predicted values from the regression model on the x-axis, their spread should be roughly the same across all values of x. In other words, the variance of the error should remain constant. In this case, the assumption is fulfilled. But what about that case? Here we observe unequal variance. At low values of x, the errors are small, while at high values, the variance of the errors becomes much larger. Number 4, normally distributed errors. The errors should be normally distributed. We can test this with a QQ plot or with analytical tests. If you like, you can check out my video Test for Normal Distribution for a deeper dive. And what about the 5th assumption, no multicollinearity? First of all, what is multicollinearity in regression? Multicollinearity means that 2 or more independent variables are highly correlated with each other. As a result, the effect of individual variables cannot be clearly separated. Why is that a problem? Let's look at the regression equation again. We have here the dependent variable and there the independent variables with the respective coefficients. For example, if there is a high correlation between x1 and x2, or if these 2 variables are almost equal, then it is difficult to determine b1 and b2. If both are completely equal, the regression model cannot determine how large b1 and how large b2 should be. This means that one independent variable can be predicted from the others with a high degree of accuracy. An example: imagine you're trying to predict the price of a house. To do this, You use the size of the house, the number of rooms, and some other variables. Usually, the size of the house is related to the number of rooms. Large houses tend to have more rooms. So these two variables are correlated. If we now include both in our regression model, the model will struggle to decide how much of the price is influenced by size and how much is influenced by number of rooms. This is because they overlap in the information they provide, and this is multicollinearity. In this case, it becomes impossible to reliably determine the regression coefficients. If you just want to use the regression model for a prediction, the presence of multicollinearity is less critical. In this context, the focus is on how accurate the prediction is, rather than on understanding the influence of the individual variables. However, if the regression model is used to assess the influence of independent variables on the dependent variable, there should be no multicollinearity. Okay, but how do we detect multicollinearity? If we look at the regression equation again, we have the variable x1, x2, and up to variable xk. We now want to determine whether x1 is nearly identical to any other variable or a combination of the other variables. For this, we simply set up a new regression model. In this regression model, we take x1 as the new dependent variable and keep the others as independent variables. If we can predict x1 accurately using the other independent variables, x1 becomes unnecessary. Its information is already captured by the other variables. We can now do this for all other variables. So we estimate x1 by using the other independent variables, we estimate x2 by using the other variables, and we estimate xk by using the other independent variables. Okay, but what is a method to detect multicollinearity? For all k regression models, we calculate r squared, which is the so-called coefficient of determination. What is the coefficient of determination r squared? If x1 is the dependent variable and the other independent variables are used as predictors, r squared explains how well the independent variables explain the variability of the dependent variable. Therefore, a high r squared in this context suggests that x1 is highly correlated with the other independent variables. This is a sign of multicollinearity. Using r squared, we can calculate the tolerance and the variance inflation factor, short VIF. Basically, the VIF is 1 divided by the tolerance. If the tolerance is less than 0.1, it indicates potential multicollinearity and caution is required. On the other hand, a VIF value greater than 10 is a warning sign of multicollinearity, requiring further investigation. Typically, statistical programs like DataTab provide the tolerance and variance inflation factor (VIF) values for each independent variable. Okay, but how to address multicollinearity? There are two common ways to address multicollinearity. Number 1. Remove one of the correlated variables. So choose the variable that is less significant and remove it. Or number 2, combine variables. Create a single variable by combining the correlated variables, e.g., taking an average. If you're using DataTab and calculate a regression, you just need to click on Test Assumptions. Here you can see the table with the tolerance and the VIF. Alright, let's work through an example on how to calculate a multiple linear regression and then look at how to interpret the results. Our goal is to analyze the influence of age, weight, and cholesterol level on blood pressure. So blood pressure is our dependent variable, while age, weight, and cholesterol level are our independent variables. To calculate the regression, we just go to datatab.net and copy our data into the table. If you like, you can load the sample dataset using the link in the video description. We want to calculate a regression, so we click on Regression. Now we simply click on blood pressure under dependent variable and age and weight and cholesterol level under independent variable. Afterwards, we automatically get the results of the regression. We will now discuss how to interpret the individual tables. If you need an interpretation of your individual data, you can just click on AI interpretation at each table and you will get a detailed explanation of your results. And if you want to test assumptions, just click here. But back to the results. Let's start with the most important table, the table with the regression coefficients, and then take a closer look at the model summary table. We will focus on these three columns. Here we can see the three independent variables, age, weight and cholesterol. The first row represents the constant. So in our regression equation, let's replace x1, x2 and x3 with their corresponding names. So we want to predict blood pressure based on a person's age, weight and cholesterol levels. Okay, in the first column, we see the unstandardized regression coefficients. These are our coefficients from the regression equation. Now we can calculate the blood pressure for a given person. Let's say a person is 55 years old, has a weight of 95 kg and a cholesterol level of 180. Then our model would predict a blood pressure of 91. So for example, if we look at the variable age, 0.26 means that for each additional year of age, the blood pressure increases by 0.26 units, assuming other variables remain constant. And what about the standardized coefficients? The standardized coefficient tells us the relative importance of each independent variable after standardizing the variables to the same scale. Why is this useful? Our model includes variables measured in different units, such as age in years, weight in kilograms. Comparing their unstandardized coefficients can be misleading because these coefficients are influenced by the units of measurement. For instance, if weight is measured in tons, the coefficient would be larger. If we measured in grams, it would be smaller. Additionally, the values for age in years are generally smaller than the values for cholesterol. So you cannot directly compare their unstandardized coefficients with each other. In contrast, the standardized coefficient remains consistent regardless of the units. This allows for direct comparison of the relative effects of different variables. For example, we can see that cholesterol level has the largest standardized coefficient, indicating that it has the strongest influence on blood pressure. In our video about simple linear regression, we explained the p-value in detail. The interpretation is similar in multiple linear regression. To summarize, the p-value shows whether the corresponding coefficient is significantly different from zero. In other words, it tells us if a variable has a real influence or if the result could just be due to chance. If the p-value is smaller than 0.05, it means the difference is significant. In our case, all p-values are smaller than 0.05, so all variables have a significant influence. Perfect! Let's move on to the next table, the model summary table. First, we get the multiple correlation coefficient R. R measures the correlation between the dependent variable and the combination of the independent variables. What does that mean? Here we have the equation for linear regression. Once the coefficients are determined, we can sum all up and calculate the predicted values y hat of the dependent variable. So if we use our example data, we have the real blood pressure data and we can predict the blood pressure data with the regression model. The multiple correlation coefficient R is now the correlation between the predicted values y hat and the actual values y. In other words, the multiple correlation coefficient R indicates the strength of the correlation between the actual dependent variable and its estimated values. Therefore, the greater the correlation, the better the regression model. In our case, an R value of 0.27 indicates a strong positive relationship. Okay, and what about R squared? R squared is called the coefficient of determination. R squared indicates the proportion of variance in the dependent variable that is explained by the independent variables. The greater the explained variance, the better the model's performance. For example, an R squared value of 1 would mean that the entire variation in blood pressure can be perfectly explained by the variables age, weight, and cholesterol level. However, in reality, this is rarely the case. An R squared of 0.52 means that 52% of the variation in blood pressure is explained by the model. What is the adjusted R squared? The adjusted R squared accounts for the number of independent variables in the model. This provides a more accurate measure of explanatory power. When a model includes many independent variables, the regular R squared can overestimate how well the model explains the data. In such cases, it is recommended to consider the adjusted R squared to avoid overestimation. Okay, and what about the standard error of the estimate? The standard error of the estimate measures the average distance between the observed data points and the regression line. A standard error of the estimate of 6.6 indicates that, on average, the model's predictions deviate from the actual values by 6.6 units. So if we predict a person's blood pressure using their age, weight, and cholesterol level, our prediction will, on average, deviate by 6.6 units from the person's actual blood pressure. Okay, if you want an interpretation of the other tables, simply click on AI interpretation. Earlier in this video, I mentioned that independent variables in regression analysis can be nominal. Okay, but what are nominal variables? Nominal variables are variables with different categories like gender with male and female or vehicle type. But how do we use nominal variables in a regression model as independent variables? Let's keep things simple. Let's start with variables with two categories. Imagine we have the variable gender with the categories male and female. Now we can code female as 0 and male as 1. The category coded with 0 is our so-called reference category. Alright, let's take a look at the regression equation. Suppose the variable x1 represents gender, then b1 is the regression coefficient for gender. But how do we interpret b1? We said 0 is female and 1 is male, so let's just insert this for x1. For a female individual, we have 0 multiplied by b1, and for a male individual, we have 1 multiplied by b1. Accordingly, b1 represents the difference between males and females. Now that we've discussed how to handle variables with two values, let's explore how to approach variables with more than two values. Let's say we want to predict the fuel consumption of a car based on its horsepower and vehicle type. To keep it simple, let's say there are only three vehicle types: sedan, sports car, and family van. Thus, we have a variable vehicle type with more than two categories. However, as we know in regression, we can only include variables with two categories. So what's the solution? This is where dummy variables come into play. Dummy variables are artificial variables that make it possible to handle variables with more than two categories. For the variable vehicle type, we create a total of three dummy variables: is sedan, is sports car, and is family van. Each of these dummy variables has only two possible values, 0 or 1. A value of 1 indicates the presence of the specific category, while a value of 0 indicates its absence. Instead of having one variable with 3 categories, we now have 3 variables with 2 categories each. These newly created dummy variables can be included in the regression model. Okay, but what does this mean for our data preparation? Initially, we have one column labeled vehicle type, where the individual vehicle types from our sample are listed. The first entry is sedan, the second is also sedan, the third is a sports car, and so on. From this column, we create 3 new variables. For the first vehicle, which is a sedan, we assign 1 under the sedan and 0 under the others, as it's neither a sports car nor a family van. Similarly, the second vehicle is also a sedan. The third vehicle, however, is a sports car, so you assign a 1 under sports car and 0 under the others. By doing this, we've successfully created our dummy variables. One important thing to note: the number of dummy variables you create will always be the number of categories minus 1. So in our case, we have 3 categories, so we basically only need 2 dummy variables. Why is that the case? If we know a vehicle is a sedan, we automatically know it is neither a sports car nor a family van. Similarly, if we know it's a sports car, we can infer that it's not a sedan or a family van. Finally, if it's neither a sedan nor a sports car, we know it must be a family van. This means we can express the same information with just 2 variables instead of 3. Including all 3 variables would make the regression model overdetermined. Okay, but don't worry, if you're using DataTab, it will automatically create the dummy variables for you. For example, if we select fuel consumption as the dependent variable and horsepower and vehicle type as the independent variables, we can then see the 3 categories here and can select which one to use as the reference category. For example, if we choose sedan as the reference, dummy variables will be created for sports car and family van. When we examine the results, we will see the 2 variables, vehicle type sports car and vehicle type family van, along with horsepower. So far, we focused on linear regression, where our goal is to predict a continuous variable like sales or house prices. But what if we need to predict categories instead, like whether a customer will buy a product or not, or whether an email is a spam? That's where logistic regression comes into play. So, in the next section, we'll explore how logistic regression helps us model binary outcomes and make probability-based predictions. Let's jump in. What is a logistic regression? How is it calculated? And most importantly, how are the results interpreted? Let's start with the first question. What is a regression? In a regression analysis, you want to infer or predict an outcome variable based on one or more other variables. Okay, so what about logistic regression? A binary logistic regression is now a type of regression analysis used when the outcome variable is binary, meaning it has 2 possible values like yes or no, success or failure. Let's look at an example. Let's say we are researchers and we want to know whether a particular medication and a person's age have an influence on whether a person gets a certain disease or not. So the outcome we are interested in is whether the patients developed the disease or did not develop it. And our independent variables are medication and age of a person. Now, with the help of a logistic regression, we want to infer or predict the outcome variable based on the independent variables. Okay, but what is the difference between a linear and a logistic regression? In a linear regression, the dependent variable is a metric variable, e.g. salary or electricity consumption. In a logistic regression, the dependent variable is a binary variable. So, with the help of logistic regression, we can determine what has an influence on whether a certain disease is present or not. For example, we could study the influence of age, gender, and smoking status on that particular disease. In this case, 1 stands for diseased and 0 for not diseased. We now want to estimate the probability that a person is diseased. So our data set might look like this. Here we have the independent variables and there the dependent variable with 0 and 1. We could now investigate what influence the independent variables have on the disease. If there is an influence, we can predict how likely someone is to have a disease. Okay, but why do we need logistic regression in this case? Why can't we just use linear regression? A quick recap. In linear regression, this is our regression equation. We have the dependent variable, the independent variables, and the regression coefficients. However, our dependent variable is now binary, taking on the value of either 0 or 1. Regardless of the values of the independent variables, the outcome will always be 0 or 1. A linear regression would now simply put a straight line through the points. We can now see that in the case of linear regression, values between minus and plus infinity can occur. However, the goal of logistic regression is to estimate the probability of occurrence. The value range for the prediction should therefore be between 0 and 1. So we need a function that only takes values between 0 and 1. And that is exactly what the logistic function does. No matter where we are on the x-axis, between minus and plus infinity, only values between 0 and 1 result. And that is exactly what we want. The equation for the logistic function looks like this. Logistic regression now uses the logistic function. For that, the equation of the linear regression is now simply used. This gives us that equation. This equation gives us the probability of the dependent variable equal 1 given specific values of the independent variables. What does this look like for our example now? In our example, the probability of having a certain disease is a function of age, gender, and smoking status. Next, we need to determine the coefficients that help our model best fit the given data. This is done using the maximum likelihood method. For this, there are numerical methods that can solve the problem effectively. A statistics program such as DataTab therefore calculates the coefficients. Alright, let's work through this example on how to calculate a logistic regression and then look at how to interpret the results. To calculate the regression, we just go to datatab.net and copy our data into this table. If you like, you can load the sample data using the link in the video description. We want to calculate a logistic regression, so we just click on Regression. We choose disease as the dependent variable and age, gender, and smoking status as the independent variables. DataTab now calculates a logistic regression for us. Depending on how our dependent variable is scaled, DataTab will calculate either a logistic or a linear regression under the tab Regression. Since we have 2 categorical variables, we can set the reference category. We will just use female and non-smoker as reference. Now we can choose for which category we want to build the regression model. So we can decide if we want to predict if a person is diseased or not diseased. Instead of diseased and not diseased, we could of course also have 1 and 0. Okay, before we go into detail about the different results, a little tip. If you don't know how to interpret the results, you can also just click on Summary in Words. A logistic regression analysis was performed to examine the influence of age, gender male, and smoking status smoker on the variable disease to predict the value diseased. Logistic regression analysis showed that the model as a whole was significant. And then comes the interpretation of the different independent variables. Further, you can click on AI interpretation at the different tables. We will now carefully go through each table step by step to ensure everything is clear to you. Let's begin at the top. First, we get the result table. Here we can see that a total of 36 people were examined. With the help of the regression model, of these 36 persons, 26 could be correctly assigned. That is 72.22%. Next is the classification table. This table shows how often the categories not deceased and deceased were observed and how frequently they were predicted. In total, not deceased was observed 16 times. Among these 16 individuals, the regression model correctly classified 11 as not deceased, while misclassifying 5 as deceased. Of the 20 deceased individuals, the regression model misclassified 5 as not deceased and correctly classified 15 as deceased. But how do we determine whether a person is classified as deceased or not? As mentioned earlier, logistic regression provides the probability of a person being deceased. So we obtain values ranging from 0 to 100%. Now we simply set a threshold of 50%. If a value exceeds 50%, the person is classified as deceased. Otherwise, they are classified as not deceased. Of course, you can choose a threshold other than 50%. To learn more about this, check out our video on the ROC curve. So let's have a look at the next table. The chi-square test evaluates whether the model as a whole is statistically significant. For this, two models are compared. In one model, all independent variables are used, and in the other model, the independent variables are not used. Now we can compare how good the prediction is when the independent variables are used and how good it is when the independent variables are not used. The chi-square test now tells us if there is a significant difference between these two results. The null hypothesis is that both models are the same. If the p-value is less than 0.05, this null hypothesis is rejected. In our example, the p-value is less than 0.05 and we assume that there is a significant difference between the models. Thus, the model as a whole is significant. Next comes the model summary. In this table, we can see on the one hand the -2 log likelihood value, and on the other hand, we are given different coefficients of the determination R squared. R squared is used to find out how well the regression model explains the dependent variable. In a linear regression, the R squared indicates the proportion of the variance that can be explained by the independent variables. The more variance can be explained, the better the regression model. In a logistic regression, however, its interpretation differs and multiple methods exist to calculate R squared. Unfortunately, there's no consensus yet on which method is considered the best. DataDep gives you the R squared according to Cox and Snell, according to Nagel-Kerke, and according to McFadden. And now comes the most important table, the table with the model coefficients. The most important parameters are the coefficient B, the p-value, and the odds ratio. We'll now discuss all three columns. In the first column, we can read the calculated coefficients from our model. We can insert these into the regression equation. So we get the coefficients for age, gender, smoker, and the constant. For example, for a person which is 55 years old, is male, and is non-smoker, we get a probability of 36%. Thus, it is 36% likely that a 55-year-old male non-smoker is deceased. In reality, there would certainly be many other and different independent variables. Okay, but what about the p-value? So, the p-value shows whether the corresponding coefficient is significantly different from 0. In other words, it tells us if a variable has a real influence or if the result could just be due to chance. If the p-value is smaller than 0.05, it means the difference is significant. In our case, all p-values are greater than 0.05, indicating that none of the variables have a significant influence. And finally, the odds ratio. But what are odds and what is the odds ratio? Let's start with the odds. Let's say we have two possible outcomes of something, success and failure. For example, if a therapy is successful or not. Let's say that the probability that the therapy is successful is 0.7, so 70%, and thus the probability of failure is 1 minus 0.7, so 0.3. Okay, but what about the odds? Odds are defined as the ratio of the probability of success and the probability of failure. Or in other words, odds represent the ratio of the probability of an event happening to the probability of it not happening. If we look at our example, the odds are 0.7 divided by 0.3, which equals 2.33. This means the event success is 2.33 times more likely to happen than not. So odds give us a measure of the likelihood of an event happening versus it not happening. In this case, we've calculated the odds of success. Of course, we can also calculate the odds of failure. Alright, now that we understand odds, let's talk about odds ratios. So what are odds ratios? Let's look at the example from the beginning. We are studying a new medication to reduce the risk of a certain disease. So we have a group A, patients with medication, and a group B, patients without medication. Let's say in group A we calculated a probability of 60% or 0.6 of getting diseased. So the odds of getting diseased is 0.6 divided by 0.4, which is 1.5. Again, odds just represent the ratio of the probability of an event happening to the probability of it not happening. In our case, in group A, the likelihood of being diseased is 1.5 times higher than the likelihood of not being diseased. Let's say in group B, where the patients didn't get the medication, the probability of getting diseased is 80% or 0.8. So the odds in group B of getting diseased are 0.8 divided by 0.2, so 4. Therefore, in group B, the likelihood of being diseased is 4 times higher than the likelihood of not being diseased. What about the odds ratio? With the odds ratio, we can now compare the two groups. To do this, we can compare the odds of getting the disease in group A relative to the odds of getting the disease in group B. So the odds ratio is simply calculated by dividing the odds in group A by the odds in group B. This results in an odds ratio of 0.38. The odds ratio of 0.38 means that the odds of being diseased in group A are 0.38 times the odds of being diseased in group B. Of course, we can also switch the order. Then the odds ratio would be the odds in group B divided by the odds in group A. In this case, the odds ratio of approximately 2.67 means that the odds of being diseased in group B are 2.67 times higher than the odds of being diseased in group A. So an odds ratio is simply a comparison of the odds of an event occurring in two different groups. The odds ratio indicates how much more likely the event is to occur in one group compared to the other group. If the odds ratio is greater than 1, the event is more likely to occur in the first group. If it is less than 1, the event is less likely in the first group. Okay, now let's put it all together and look at how to interpret the odds ratio in logistic regression. Let's get started. First of all, to calculate a logistic regression, we need data. Let's say we have data from 50 patients. Our outcome variable is disease, which is coded as 0 for not diseased and 1 for diseased. And we have two independent variables, medication and age. Now we can use this data to calculate a logistic regression. You can find a link to the dataset in the video description. In the first column, we can see the coefficients that define our model. These coefficients can be entered into the logistic regression formula. Here we can see the coefficients from the table: the constant, the coefficients for medication and for age. Now we just need to enter a value for medication, such as 1, indicating the patient received medication, and a value for age, for example 50. Then we can calculate the probability. In this case, the probability of being diseased is 0.55 or 55%. So for a patient who took the medication and is 50 years old, the probability of being diseased is 55%. Of course, we can simply use DataTab to calculate this probability. To do this, just enter 1 here and 50 there. We will then also get a probability of 0.55. And DataTab further gives us the odds. As we know, the odds are calculated by the probability that a certain event will happen divided by the probability that the event will not happen. We therefore get 0.55 divided by 1 minus 0.55, which equals 1.22. Okay, but we are not interested in the odds alone. We are interested in the odds ratio. Again, the odds ratio is simply a comparison of the odds of an event occurring in two different groups. The two groups could be persons who took the medication and persons who did not take the medication. Therefore, if we're going back to DataTab, we just need to compare the odds of a person who took the medication with the odds of a person who did not take the medication. So to get the odds ratio, we just need to divide the odds of a person who took the medication by the odds of a person who did not take the medication. This results in an odds ratio of 0.64. And surprise! The calculated value matches the odds ratio listed for the variable medication. The odds ratio of 0.64 for medication indicates that for individuals who took the medication, the odds of the outcome diseased are 0.64 times the odds of those who did not take the medication. Alright, with medication we have two groups to compare. But what about a continuous variable like age? In this case, we simply look at what happens when we increase age by 1 unit. For example, we might compare the odds of the outcome for someone aged 50 versus someone aged 51. This allows us to calculate the odds ratio by comparing the two odds. In this case, we get an odds ratio of 1.04. So for each 1 year increase in age, the odds of the outcome diseased increase by a factor of 1.04. But there's one thing I haven't told you yet. The odds ratio can actually be calculated simply by exponentiating each coefficient. So e to the power of 0.45 is 0.64, which is the odds ratio of medication. And e to the power of 0.04 is 1.04, which is the odds ratio for age. To sum it up, odds are simply the ratio of the probability of an event happening to the probability of it not happening. The odds ratio is now the ratio of the odds that an event occurs in two different groups. Great! We started with the fundamentals, explored simple and multiple linear regression, and finally we tackled logistic regression for categorical variables. By now you should have a solid understanding of how regression works and how to apply it to real-world problems. Thanks for watching and happy learning!